All right, welcome everyone. This is part 3. We should be wrapping up this particular tutorial from KDD on inference optimization. It says for foundation models, but really we're talking about language models, LLMs, on AI accelerators. And so I mentioned this the last 2 weeks, and I will say it again that this is the group that put together this tutorial. These are not our slides. We're following their roadmap, and so they did an excellent job. We're very grateful for the people that put in um, all the work to put all of this information in one place and have great links. Almost all of the slides that have references to a particular paper or technique or whatever have a link in tiny print at the bottom where you can go and read about it. So uh, not going to spend obviously the same amount of time that we did the last couple weeks, but I just wanted to blitz through the slides just to orient for people who weren't here the last couple weeks. So basically, no surprise, LLMs are getting bigger. Everybody knows that, these models like GPT-4, are huge. And basically, they're making an argument that despite the fact that it really took crazy amounts of resources, potentially hundreds of millions of dollars and all that to train some of the largest models, uh, because we now have millions of users a day hitting a lot of these models, it's actually far more compute that's going towards inference than went to the training. And so uh, um, it's certainly a problem that is well worth optimizing. So after that, then basically it says, okay, here's this outline. We're going to talk a little bit about what are hardware accelerators, GPUs, and other similar devices, and what are the things that we optimize with architecture and system level changes. And then today, what we're going to talk about is this last part about model compression and speculative decoding. They have a couple case studies that wasn't planning on covering, just sort of the core material here. So quickly, so in terms of LLMs, if you guys are doing ML at all, you've heard of the transformer. Here's our basic transformer, and then there's different variants of it. So the original one had an encoder and a decoder, um, like this, but then you have things like BERT that's only an encoder, and then most of the LLMs that we talk about, your llamas, GPT-4s, Mistral, Claude, they're decoder only models. They only have the part in the pink, less this part here. And when they're using autoregressive masking of the attention, then that creates certain properties that people are able to take advantage of to really optimize inference. So we talked very briefly review of attention. So attention means that basically at any token position, you can look back at all the other token positions. You're going to calculate queries, you're going to calculate keys. And what we saw later on is that essentially once you calculate the key for the third token, that vector of floating point numbers is going to be the same. So whether you're currently outputting the 10th token or the 10,000th token, the keys and the values for token 3 are always the same. And so this eventually we'll see later on in slides leads to the fact that you can actually cache these. You don't have to recompute them from scratch every time you spit out next word. So a whole bunch more stuff on the attention calculation. In Llama, they do actually have something slightly different than the original Vaswani transformer, which is just 2 weight matrices. There's this gated business, which if you're familiar with Mamba, looks this is sort of the same structure there. So it ends up having 3 weight matrices in the MLP feed forward part. But otherwise, it's pretty similar. And so then if we just keep going through, advancing here, when you use an LLM, a decoder-only LLM like ChatGPT, then basically it's always going to predict the next token. If you have a long prompt, I think the example I shared is, hey, you're an expert on helping people finding jobs. Here's all the text in my resume. Can you make suggestions for how I should update some of the text, update some of the bullets, make it more attractive sounding? So then if it's a 3-page resume that I'm pasting in a little on the long side, then maybe I have a couple thousand tokens or whatever. Uh, there is no need for, say, the 10th token to predict the 11th token. There's no need for the 1000th token to predict the 1001st token, because no matter what your prediction is, I've already given you what the first 3000 tokens are. You know, it's again the prompt that I just said plus all the text of my resume and then whatever. So because you don't actually care about the predictions, you can actually run the computation of all the queries, keys, and values on the prompt part, the first 3000 tokens. You can run all of those in parallel, however you feel like. You can do it all at once, or you can do it in chunks and stages, whatever. But you really can do it, and so that's why we talk about this pre-fill stage. It's going to be highly dense computation, and it can all be done at once. Once you get to the end of the prompt, which I'm saying was 3000 tokens, then you predict the 3001st token, and you cannot do any more. You have to actually wait till you finish that prediction. Then you concatenate that so that now you have 3001 tokens, and then you predict the 3002nd token. And then once you've picked that one, then you concatenate that at the end. And so then this decoding stage has to be one token at a time. And there's we'll get to speculative decoding at the end, but in it, normally speaking, there is no real shortcut for this. And so what we will see is that the computing patterns are very different in the pre-fill stage, where you can do hundreds or thousands of things potentially all at once, versus you're really forced to only just do one. So then we get into a little bit more details, and then ultimately what we see is that, again, that the keys and values in the pre-fill stage, that in this case, let's say it's 3000. Those 3000 keys and values from my prompt are going to stay the same when we're outputting the 3001st, 3002nd, 3003rd, even if we are outputting the 4000th token. The keys and values for the first 3000 token positions are never going to change. And so there's a whole bunch of strategies that we talked about last week in terms of how you can cache these and how you can try to optimally sort of pair your cache and your pre-fill time and your decoding time. So then a little bit about going back. I can't. Um, Here's the complexity. The main thing to see is that you have this LD squared component and this L squared D. So D is the dimensionality of your model. So when the model gets bigger, this number goes up quadratically. When your sequence length goes up, this L squared part goes up quadratically. And so that's why it's so much harder to support 100,000 length tokens than 32,000. Because even though it's only 4 times longer, you're actually doing a 16-fold increase in this particular component. So um, uh, at points, it gets quite prohibitive. So then a bunch of slides talking about the KV cache, memory requirement, and whatnot. So very quick tour through. Then we looked at GPUs, and basically what it says is, hey, we've got a bunch of different data types, and we've got computing units that specialize in these different things. And in particular, we are going to have tensor engines that do matrix multiply. Sometimes you'll have something that's like matrix vector or vector vector, but all GPUs, all TPUs, whatnot, are going to have things that do matrix multiply. And so in a perfect world, you want large matrices, and you want to be able to sort of pile them up and keep this tensor engine busy. So then some different architectures. So when we talk about optimizing, we've got some different metrics. So you could look at the time to the first token, time between each token. You can look at end to end, and you can also talk about like throughput, which kind of matters to users. If I say I have a million things that I want all to like score on your model, and it also matters to you if you're the model serving. Obviously, if you have a server, the higher the request rate, the more people you can serve per second, then the more money you're going to get, more revenue from those users, and the fewer servers you need to buy. So then a bunch of different things here listed, and we went in and talked a little bit. Again, I told you going through here super fast. Jerry's back in town, so I just got him the raw recordings from the last 2 weeks, so we'll get those up to YouTube if you want to actually see any of these in more detail. So instead of calculating every query and multiplied against every key, what you can do is you can reduce the number of queries and you can group so that multiple tokens are sharing one query. And if you group two tokens together, then that cuts in half the number of calculations you need to do. If you group four of them together, it's a factor of four. So it's actually a pretty big savings when you are really like cutting it by, you know, um, a multiple.
Hey,
Mixture
Ted.
of experts. Yeah.
Yeah, just quick
Just
comment
quick
on that
comment.
last,
Yep.
the mixture or the group query attention. I did look this up, and they're basically doing an averaging of the weights for the two queries. So it is kind of like a superposition.
Yep. That's cool. Yeah, I figured, right, you're not going to like ignore one. So there's a
Yep.
little bit of extra work you need to do to average these, but then ultimately you have a half size or quarter size matrix multiply. So then it's quite a bit cheaper. Cool. Thanks, Roger. Um, so that's the attention part. Another thing you can do with the MLP part is you can have a bunch of MLPs, but only use a small number of them, one or two at any given time. And so then Mixtral is probably the most well-known model that uses this. Um, okay, so then we talked a little bit about um, can we optimize the forward computation? Can we, if we have a GPU, can we optimize its use, get it closer to 100%, and then leveraging some special properties of these decoder-only LLMs to improve inference? So first thing we talked about is there's flash attention, which basically says, hey, if I have to do queries times keys and I have to do softmax and then I have to multiply it um, by another matrix to get the values, to get the output, instead of reading and writing from memory every time, it'd be nice if I could just fuse these three operations together and then skip basically doing this write and then follow by reading the same thing back. The problem is people aren't dummies. The reason why they don't fuse these three together is because it gets so big, it doesn't fit in the GPU anymore. So in flash attention, one of the key things they do is they end up breaking up this operation into smaller tiles where you can do all three of these things at once on each tile. And then there's a little bit of overhead to stitch together the tiles. But in the end, for large, dense operations, this is a win. So this works well during prefill, and this works very well when you're training LLMs. Generally speaking, the way people train them, it's like prefill with the maximum sequence length all the time. So they do it for both the forward pass and then flash attention. Also, you can do the gradients, the back propagation in a very efficient way. There's a different, oh, sorry, a couple more slides. Um, when you get to the decoding stage, because you're only predicting one token at a time, assuming you cache all of the old keys and values, you only have to do one query times um, um, the keys and values, and that's not it, to you or me doing it like by hand on paper and pencil would be something, but for GPU, that's really not a lot of compute. And so you cannot keep a GPU busy just doing one query at a time. So one of the things, one technique that come up with is flash decoding, where basically you split up this query times the various keys um, into smaller chunks, and then you can actually parallelize them and feed them all at once. So that's a way to actually speed things up on just the decoding side. You also then we talked about very, very briefly, different ways that you can do parallelism across multiple GPUs, multiple instances. You either divide up the matrix into different chunks, or you can take like the model, divide it up into different chunks and do layer one on one server, layer two on another server, that sort of thing. There's multiple different ways you can divvy it up. But if you divvy it up so there's minimal communication needed between the different pieces, then you get almost linear scaling. Okay. Um, So the next thing we talked about last week is this idea of continuous batching. So naively, if you just did static batching, you would say, okay, let's say I've got enough resources on my GPU to do 4 users at once. So then you're going to start completing, answering people's prompts. And then the vanilla way is you would basically wait until whichever one of them has the longest answer. And then when it ends, then you're going to bring in a set of new 4 users and you'll do all of them. But so you see there's this white space that's sort of this unused GPU capacity. And so the idea is instead of waiting, as soon as the first user has finished their response, you get end of sequence, you can then begin the next part of the next user. It requires you managing masking and stuff so that you do it right. But ultimately, if you do that, then you can always have 4 users active at any point in time. Again, it's a little bit trickier to manage because the 4 users did not all start at the same place. But nevertheless, you do a little bit of bookkeeping and it can be done. Yeah, raised hand. Dave?
So I just wanted to highlight that the yellow part is the pre-fill, and the blue part is the single token decoding here.
Yes, yes. And one of the things we talked about is that each of these vertical columns represents like sort of one time chunk. So it's not necessarily one token or one whatever, but basically what we're saying is instead of waiting until the last user in your batch finishes to start 4 new users, as soon as any one user finishes, just go ahead and start a new user there.
So
Um,
we had this discussion last time also. Given that GPU is a single instruction, multiple data format processing, the processing is changing across multiple these batches here, right? So at T4, S1, S2, S3 are doing the blue operation, and S4 is
mhm,
still doing the refill operation.
mhm.
So could you elaborate again how that is handled?
So the operation they're doing is exactly the same. They're still doing the attention operation of query times key. It's just that in the blues areas, maybe you're doing, say, 1,000 queries at a time times your keys, whereas in S4, there's only one query. Oh, sorry. Yellows, you're doing 1,000 queries at a time. When we get to blue, then it's just one query. But mathematically, it's exactly the same.
Okay, so the data that is coming in would, depending on KV cache, depending on many other factors, will keep changing here. But the operation is still trying to run through the layers of
Yeah,
your transformer
yeah,
blocks.
yeah. So when you're in the yellow, basically what you're going to do is you're going to have a whole bunch of keys. Sorry, you're going to have a whole. You, let's get the terminology right. So you have an input to an attention layer. Okay, so you're going to have a whole bunch of inputs. You're going to multiply that input by your key weight matrix, and then you will get actual keys. Okay. You're going to multiply that weight matrix by all your queries, and you're going to get a whole bunch of queries. Then you're going to do a giant matrix multiply of all the keys by all the queries. And then later on, you'll do softmax and stuff in order to calculate all of your attention scores. Okay. By the time you get to the blue part, what you're going to have is almost all of your keys are going to come from the cache, and you're only going to be calculating one key and one query for the most recent, the latest token position. And then once you have that, then you can do the attention calculation of that query against all keys, both current and historical. So you're still basically just doing a whole bunch of matrix multiplies. Yeah. So what's different is whether or not you have one new query and key, or whether you say have 1,000 new queries and keys. So either
And
way,
whether
it's
you,
KV cache plus the new stuff. It's just the new stuff might be in the blue tiny, it's only one, or in the yellow, the new stuff is going to be big and wide to try and fill up your, you know, your GPU's matrix multiply engine.
yeah. And then as you can imagine, or as one can imagine, a lot of engineering goes on at this lower level to optimize the throughput and memory accesses and whatnot. But yeah,
Yeah,
thank you.
yeah. Yeah, and on any given GPU, you need to kind of figure out how much memory is your KV cache taking and how long does it take to do the matrix multiply versus this versus that. So choosing like the optimal blend, yes, that's uh probably not easy, but at least conceptually we can say that the idea is fairly straightforward, that you just, you know, throw stuff in here like the bottom diagram. And so eventually, instead of having a nice, pretty, you know, what we think of as just like a simple triangular, uh, um, you know, shaped masked attention or whatever, you're going to have this weird thing where you're going to have these block diagonal things because you're going to have different users starting at different times. And so this attention mask is going to get a little more complicated looking. Okay. But other than that, again, you do some bookkeeping and ultimately you figure out what this has to look like. It's not the end of the world. Um, and so in the worst case scenario, you can imagine where one user is outputting something that's, you know, 50,000 tokens, and these other users had things like, what's the capital of France? And then the capital of France is Paris, and so it's like 10 tokens. In this simplistic case, the other 3 user slots after the first 10 tokens are all just going to be sitting idle while this one user with a really long response is generating 50,000 tokens. And so your GPU is going to be roughly 3/4 unused because it got to be busy for a very short period of time. And then, you know, here you see it's only like 1 or 2 longer than the other guys. But imagine it was 50,000 longer, then that's a really terrible waste of resources. So then in theory, during that 50,000, you could have, those other 3 user slots, you could have not only put in another user, but they might have finished, and then another user after them, and then another user after them. So you could have actually had like 3,000 different users that all completely got serviced during the time it took you for this one super long response to finish. So that's the idea with continuous batching. And again, there's some definite difficult, complex bookkeeping that you need to do in code you need to write. A similar phenomenon we talked about is, okay, you got this KV cache, that's great. I don't have to recompute these keys, but I do have to store them around, and they do take a bunch of memory. And if all of the users in your batch, you go to the full length, then you're wasting a whole bunch of memory because some of them are short, like what's the capital of France? And so then basically, just like memory can be managed with pages on a general computer, GPU memory can be managed with pages on a GPU. And so that's the idea here, is that they do chunks. And so the smaller the pages, the less you waste within a page, but the more bookkeeping you need to do. So somebody's got to figure out what's the optimal page size for this. And again, I don't know exactly how all the details work, but I do know that at least conceptually, it's easy enough to say we're gonna page this. And then we've got some diagrams here that show how basically now the different tokens are no longer contiguous in real physical memory. They're just given contiguous virtual addresses. Chunk prefill is one of my favorite concepts. And the idea is that if you have a very, very long prompt, let's just say, pretend for now that my resume example with 3,000 tokens is very long. Maybe these days it's not considered very long. If if that's this green box down here, then once I tell the GPU, once I initiate go and do the pre-fill and calculate all the keys and values for these 3,000 tokens, at that point, the GPU is going to chunk away and basically um, I can't really add any new users. It's just chunking away on that one giant math problem. Okay. But so what they're saying is that if you break this up into smaller chunks, so like I broke this up into 3 individual chunks of 1,000 tokens each, after the first 1,000 part of the matrix multiply finished, I could potentially add new users, these 2 blue new users in here, and have them run in parallel with my second chunk. And then I could add another 2 users. And so the general idea is that because prefill is very mathematically intensive, uses the matrix multiplies, there's only so much of that you can cram in a GPU. For regular decoding, it's the opposite. It doesn't fully utilize the mathematical part of it, but the longer those prompts and sequences are, it actually uses up a lot of memory, so you can't fit a lot of decoding on one GPU, even though it might not actually be doing a whole lot of flops. So the ideal thing, depends on whether your user base actually looks like that, is to actually combine a little bit of prefill with a bunch of other users that are doing decode. And so basically, depending on which way you look at it, if you're doing the prefill anyway, you can kind of get the decode for free because it's so light on math that it's basically not slowing down your prefill. Or vice versa, if you had a whole bunch of decode that you were going to do anyway, you had 5 users that you were going to do next token prediction on, they're not going to use the matrix multiply unit very heavily. So you could throw in a bunch of prefill and it won't really slow down the decoding at all because they weren't using the matrix multiply anyway. So by combining the blue and the green, you get that for you pair them and you get sort of this optimal utilization. Here's a diagram that tries to show, I don't really understand the diagram, but the idea is, yeah, one's arithmetic intense, the other's memory intense. And so if you go in the middle, then you kind of get the best of both worlds. Then the next topic was like, okay, you could do KV caching in a way that is stateful. So the thing is, if the first token in a conversation is hello, then for every user, every whatever, where the first token is hello, that hello is going to have the exact same keys and values. So then if you say hello and the LLM says back hi, then basically those first 2 tokens are going to have the exact same floating point numbers for any user where the first thing they said was hello and then the next thing the LLM said was hi. So what you can do is not only can you keep track of the keys and values for the conversation that I'm in with the LLM right now, if you keep those strings around, you can basically reuse that KV cache for any user that has the same strings at the beginning. And so you can do this in a number of different ways. And then the fancier ways is you can sort of build this tree of different like beginnings and then like, so you have hello and there's 3 different answers that could come from that and blah, 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 blah. You can basically, as much main memory as you have on your server, you can keep these things around, and it's still faster to copy these from the server to the GPU than to ask the GPU to do all the matrix multiplies to calculate them again from scratch. So it's this just caching reuse type stuff, and there's different techniques and fancier ways to do it. There's this pensive technique. And then here you see this like these radix trees built for caching all this stuff. So we have a slide here that summarizes all these different techniques and how they either reduce times the first token or throughput or whatever. Yeah, Dev?
So going back to the caching, is prompt caching the same?
Yes. So basically your any so technically speaking, like when you use ChatGPT, there's a system prompt and blah, 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 blah. But assuming the system prompt is always the same, then if I type something like, you are an expert programmer. In Python, how do you do blah, 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 blah. And then you type, you're an expert programmer. In Java, how do you do blah, 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 blah. We both had that same prefix of you're an expert programmer. So the keys and values for you are an expert pro, those 5 are going to be completely identical for your prompt and my prompt. And so theoretically, if you just kept around something that says the prefix is you're an expert programmer, then you can have a cache, a KV cache for just those 5 tokens that you can reuse over and over again for all of eternity.
Right. And
Sense?
yes, it does. It goes beyond a single user's. Many times there are prompts that you save so that this is basically your user profile or your way of responses that you want to want or expect or want the LLMs to respond. So maybe that is another example. I was
Yep.
thinking, I think you went beyond that thinking, which is your own prompts. But sometimes it could be that when I'm working on a project, let's say, right, my initial few things I copy paste from the previous query in my new chat because, I'm just changing a few things in my interaction, but instead of continuing the previous chat, because that is going to just keep on blowing up the context potentially, I just start a new chat. And I'm giving you a chat example, but it can go to other scenarios as well. So then 80% of the prompt in the beginning is same, so it doesn't have to recompute all of that. Yeah, makes sense.
Exactly. So that's the idea. And so like, for example, at work, one of the things we did was we used a vision language model and we were asking questions and then I would feed it 10,000 images, right? So when the prompt is at the beginning, that part is going to be the same, the first, whatever, 50 words, it's going to be exactly the same. And I'm going to do 10,000 inference passes. So absolutely, there's an engineering problem of like knowing, right? But if you knew that that was going to happen, you certainly would want to just sort of save the prompt for the first, the text part that I wrote. And then obviously each image is different and will get tokenized. And so those will have to be pre-filled from scratch.
Right. Great, thanks.
Cool. Thanks, Dave. All right, so then I think this gets us close to where we ended. Let's see here. There's a couple solutions. I don't know all of these. I'm familiar with VLLM. There's TensorRT-LLM, SGLang. There's different systems, and if you just look online, you'll see lots of companies claim that if you do LLM inference with the exact same model, so like Llama 370 billion or whatever, that their server will actually be faster than somebody else's server. And it's using, tricks like the stuff that we talked about. That's how they achieve a lot of these things. Okay, so that was the maybe not super duper crazy fast, but the fast recap of the last 2 weeks. So this week, now we're going to go a little bit slower. We're going to talk about the new topic, which is model compression. So subtopics here: motivation, quantization, distillation, pruning. If you're familiar with any of these topics, the techniques we're going to talk about here are really not different. It really does translate from any other place where you're doing quantization or distillation. So, so for those of you who are familiar with some of these, it really does carry over. Okay, so motivation, basically, no one here is going to be surprised that larger models perform better. So great, but the problem is that large models, the inference is expensive and it's slow. They have a couple more slides here. I don't remember exactly all the details, but so imagine you're using one of the newest Llama models, 3.1, 405 billion. If you implement this with 16-bit brain float, that's going to be 810 gigabytes just to copy the weights to memory, not even to do any work on them, just to copy them. And so there are no 810 gigabyte GPUs. You're going to have to then split it up and do parallelism, blah, 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 blah. All right. So then there's more math. one of the problems you have is it's slower decoding because it's a big model and we have to do all this math and there's probably going to be memory pressure for loading things or whatever. The prefill is slower because you're doing more flops on a bigger model. It's also, so the big idea here is, can we make the model smaller? And there's different ways that we can make the model smaller. One thing we can do is we can use lowered precision data types that physically take up less room in memory. A 16-bit float takes up obviously half the amount of space as using a 32-bit IEEE float. Okay, 8 bits is even less, 4 bits is even less. But the other thing we can do is we can use fewer parameters, and there's different ways of deciding how to do fewer. So we'll talk about both of these. Generally speaking, either of these techniques, you are going to have a trade-off. You are going to lose performance. Quality goes down when you do these. So some of the other things that we talked about in the last 2 weeks is techniques for pairing, timing, organizing, whatever, and you're still doing the exact computation, you're getting the exact performance. This third week, what we're talking about here, all of these techniques in this section do have a trade-off. And so you have to decide, how far am I going to push fewer parameters? How far am I going to push smaller data types, quantization? Because the more you push, the worse your performance falls off. So if you have a very light task, simple question answering chatbot for your website, you might be able to push it a lot because the task is really easy. If you're using this LLM as like a coding pair programmer, or to help engineers, doctors, research scientists answer cutting edge questions, you may not be able to get away with this because you need every ounce of performance you can get. So let's see here. So benefits of these techniques. Yeah, I think we kind of talked about it. So you can reduce the number of flops. In the slides, I noticed it didn't necessarily seem to talk about the fact that even if you do the same number of operations, your GPU, if it has the hardware support, can actually do many more 8-bit integer multiplies in a second than it can do 32-bit floating point multiplies in a second. So it's not just the number of operations, it's also some operations are just cheaper. So speeding up prefill and reducing memory. So you have memory in lots of different places. Memory when you're storing the weights, but then remember, every time you bring those weights into and you're doing matrix multiply and whatever, you have the opportunity to reduce the amount of memory for some of these techniques. What ends up happening is in some cases, you really need the matrix multiply to be done in at least like a 16-bit floating point precision, because the scale of the numbers can really change. So you're really not benefiting at the sort of tensor unit. You're really only kind of benefiting in terms of like main memory. So we'll see, we can look at, and then the measure that they use for compression is compression ratio. So just original size divided by compressed size. If it's half as big, then R is 2. Okay, so let's actually talk about the different techniques here. Make sure we have time to kind of get through this. So quantization. So a lot of stuff you'll see is already supporting 16-bit because people have found that if you do things well and whatnot, you can store the weights in 16-bit floating point, and there's really imperceptible drop-off in performance. So when we talk about quantization, usually we're talking about going lower than 16. So 8 and 4 are pretty common right now. And the
Hey,
good
Ted.
news is that one sec, Jerry, sorry. The good news is that lots of hardware supports these now. So so they'll actually do like 8-bit, 4-bit integer multiply really, really fast. Yeah, sorry.
Yeah,
Yes.
when you said performance, I assume you were talking accuracy of the result, not throughput, correct?
Yes, correct. Sorry. Yes, accuracy. Yeah, probably a better word to use. So accuracy of the math, and thereby ultimately accuracy of the downstream task So if you ask the LLM, you know, in Python, how would you code blah 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 blah, you'll get the same answer whether you use 32-bit or 16-bit. You'll get the same words, the same, you know, output. Once you get below 16, then people don't have a difficult time noticing that you'll start getting different answers. In some cases, the answers aren't bad. In other cases, they just flat are worse answers. Thanks. So here's an example. I don't know if we really need to go into it, but basically, you do have to understand that if you have an earlier layer and you have the activation coming out of it, then if that activation, say, floating point 16, you do need to quantize that down into an 8-bit integer in order to get the full benefit of being able to do integer matrix multiply. So you need both the weight and the from the current layer and the activation from the previous layer to both be integers in order to take advantage of this. And I don't remember exactly where, but there's a couple slides where they talk about exactly when do you convert the different data types or whatever. So in general, with quantization, you're not reducing the number of operations. You're not reducing the number of flops. But you are reducing the amount of memory. And sometimes, if you're lucky, these operations run faster. But do note that you're doing this like quantization, dequantization. And so you actually are doing slightly more operations when you do quantization, okay? So you need like the benefits to outweigh the fact that you're actually doing a little bit more work. And recently was looking at a, well, no, that's sort of separate conversation. Okay, so the really big gain is that we reduce memory quite a bit, because if you go from 16 to 8, there's half as much stuff that you need to copy in and out of the GPU. Yeah, was there a question?
Yeah, I had a quick question. A little bit of a conflict of my understanding then. So quantization of the weights, they mention here the dequantization. So you're storing it, let's say, as 4 bits, and then the dequantization, I assume, is expanding it to like a BF16 or something like that. But that's different than the prior slide where they actually showed it being quantized down into an int 8, and the multiply is actually an int 8. And so are there both techniques? Do both techniques exist, or?
Yeah, both techniques exist, and I don't know if it'll be completely clarified, but there are a couple things that we'll see where there's some more details on the next few slides.
Okay.
So hold that off till we get to the end of it. Okay. So one gory detail when you talk about quantization is, are you going to do symmetric or are you going to do asymmetric? And I don't think there's a slide for it, but you could also do perfectly like linear or equal buckets or not equal buckets. Okay. So for symmetric, if you just said, okay, I've got a big matrix, it's got 1,000 by 1,000, it's got 1,000,000 floating point numbers in there. What's the biggest? What's the smallest? Well, the biggest is 10, and the smallest in the other direction is -5. So in symmetric, you would just simply say, I'm going to have my max be 10 and my min be -10. And if we're doing, let's say, 4-bit, and we're doing the traditional, the linear, then you literally just say, I'm going to divide up this space of 20 numbers into 16. And so each one's going to be like around whatever 1 point, I don't know what I was saying, but 1.3 or something like that or whatever. And so you're going to have like 0 to 1.3, 1.3 to 2.6, and you'll have, you know, like 8 buckets over here, 8 buckets over here. And so for any given floating point number, then you are just going to assign it to the nearest number here. And then for asymmetric, you don't have to actually do that. You can, if you had +10 and -5, you can allocate more space on the positive side and less space on the negative side because you don't need to go as far. So that's one choice you can do. And then they go into some details here, but the important thing is that basically you're going to be rounding off all of your numbers to, to basically the nearest. So in this case, if I say 4-bit, the nearest of these 16 values. Okay. Typically, the way you do quantization, if you guys haven't seen this, if you're not familiar, is you have a fixed set of numbers that you're using. So like maybe for 4-bit integers, you have like whatever it is, like -7, through -1, 0, 1 through 8, and these are your 16 numbers that you can actually use. Okay, and so what you have is you have a scaling factor and you have an offset potentially, and so basically when you have your million numbers, you basically get to pick where your middle is, that's your offset, and then you pick your scaling factor. And so with those two numbers, you can convert any of these numbers from -7 to +8. You can convert any of them to an original floating point number. So it's not that like you have to have a fixed scale, like all the numbers have to be between -7 and 8. No, they might all be between, like I was saying, -5 and or -10 and +10, or they could all be between -0.1 and 0.1. So this scaling allows you to handle that. And then what we will see, as mentioned in the chat, you're going to have a real problem if you have a million numbers and 999,000 of them are between 0 and 1, and one of the numbers is a million. So now what's going to happen is you're going to need to stretch your scale to accommodate that million, and then all 999,000 of the other numbers are all going to fit in the exact same bucket, and you're going to be really wasting the fact that you have 16 different buckets. Okay, not only are you wasting the buckets, but then also what's going to happen is you are going to have large rounding errors because you're rounding everything to the nearest, whatever, 200,000 because of this one outlier number. So that is one of the core problems with any kind of bucketing or quantization. So if any of you guys have ever just done like a basic machine learning problem and you said, I want to see a histogram of my values, but you have one outlier value at a million, then what happens to your histogram? You have one bucket that has all of your normal values, and then you have all zeros, and then you have one bucket that has your one outlier in it, and it's a completely useless histogram. It's basically the same thing. You can think of like a 4-bit quantization as a histogram with only 16 bins, and so that's the worst case scenario for your 16 bins. Again, it goes into a little bit of the math of exactly how you calculate what the different bins are, but I think the idea is pretty simple, that you're just like, rounding things to the nearest matching number. So you're going to have a little bit of error from this rounding that you do. So one of the things they talk about is this granularity. So I said you have a 1,000 by 1,000 matrix, so you've got a million numbers in them. So what you could do is you could just, for this whole tensor, these million numbers, you could calculate it. But it turns out that what you can do is you can break it up into smaller chunks. And there's different ways you can break it up into smaller chunks. But so if we had this one number that was a million, whereas all the other numbers were between -1 and 1, then basically it is still going to cause problems, but it is going to cause a problem only with the chunk that it lives in. And so depending on how many chunks we divided it into, if we divided it into 100 chunks, the good news is 99 of them are not going to be impacted by this outlier, and only the one chunk will be still impacted by that outlier. So that is one simple way that you can improve this quantization. You may have figured out, though, the more chunks you have to store these scaling and potentially offset numbers And so you incur a cost in terms of the storage of those, and you also incur a cost in terms of it's hard to really parallelize all this quantization, dequantization stuff, because instead of saying, here's a million numbers, just, scale them all, multiply them all by 1.735. Now you have to do this chunk, I'm going to multiply by 1.7, this chunk I'm going to multiply by, 3.4, this chunk I'm going to multiply by 0.2, and you can't, parallelize and get as much, going through your GPU. So typically when you quantize in an LLM, this might be slightly different from other architectures of neural networks, okay? So what are the things that you might quantize? Certainly you're going to quantize the weights of the linear layers and that are inside attention and inside feed forward. So you just have regular linear matrix multiplies to calculate queries, keys, and values. And then people may not be as familiar with it because it doesn't get talked about as much, but there's a fourth one. There's an output matrix multiply there. And then the feed forward layer, traditional Vaswani, you have two very large matrices. Llama and other have this gated thing where they have three matrices. These are all just rectangular, usually square, but rectangular matrices that are doing a bunch of matrix multiplies. So certainly you can quantize those weights. You can quantize the activations, and that's potentially beneficial, but in LLMs, less true in other models. In LLMs, you tend to have more outliers in activations. So you have to pay more attention to how you quantize these. And then you have your KV cache. Since that's taking up a lot of GPU memory, it would be awfully nice if you could use a smaller data type and take up less space for the KV cache.
So if I'm not mistaken, I think for activations, they generally don't, in LLMs, they don't tend to have quantization. So
I
some drop in
believe
performance accuracy because of that.
so I believe, Dave, there's two different recipes. One recipe for training and another recipe for inference. In training, you kind of can't get away with any quantization, and people tend to not even use 16-bit, they tend to use 32-bit floating point. No quantization at all for those activations. I think during inference, you can get away with a little bit more if you do a smarter quantization technique that can deal with outliers. Then people do get away with a level of quantization on LLM inference, different recipe. So here's where things get a little bit interesting. So how do you quantize them? Okay. So one thing you can do is dynamic quantization. And so then let me just see. So you'll see the next slide talks about static quantization. Okay. I think actually it's a little bit easier to talk about static quantization. So basically static quantization says, let's say I want to quantize my activations. Well, what is the biggest value? What is the smallest value? With a weight matrix, they're just sitting there in an array and you can look at them. But for activations, how do you really know? So what you have to do is you have to run sample data through and see what is the biggest positive value and the biggest most negative value so that you can see what is the scale you want to use for your quantization. And if you're ever wrong and there's a number that's beyond, outside of those ranges, then you're going to have, in addition to all the normal sort of rounding errors, you're going to have clipping errors on those as well. But so the static basically says you kind of do this, and then you can, the good thing from an efficiency perspective is you can hard code, my biggest activation was 25. So basically, I'm just going to take all of the numbers and I'm going to divide them by 25, and I'll have numbers between, -1 and 1. Okay. Going back, in dynamic quantization, what you have to do is you have to, on the fly, say, I have let's say my model dimension is 4096. Okay. So just looking in one place, I don't have a floating point number. I have 4096 numbers that I might want to reduce their memory footprint. And so I can quantize those. And so then you can say on the fly, what is the biggest, most positive? What is the most negative of those? Set up your scale, do the quantization there. Obviously, this is more work at runtime, right? You have to scan across and find the max positive, max negative. And then you're going to do these operations with these scaling factors or whatever for quantization and dequantization. So that's why the static is in some ways attractive, because you can just figure it out in advance and hard code it. But dynamic, obviously, you're not going to run into that problem where, whoops, I thought the biggest possible number was 25, but here I am running inference on this problem, and all of a sudden a number comes in and it's 60. And so now I'm going to be having an even bigger error in my numbers because of that. Another choice you have is this idea of post-training quantization or quantization-aware training. I don't know if I can explain this exactly how it works. Post-training quantization is pretty straightforward, okay? You train the model just like normal. You can do this with a model that somebody else trained. So somebody trained Llama 3.2, and you just have the model. And now you're going to apply something after the fact, okay? So this is pretty cheap. It doesn't really require anything. Unfortunately, you have all of these rounding errors, and what will happen is, in terms of like law of large numbers, many of them will cancel out. The nature of LLMs is that they have a small number of very large values. Outliers are not a random phenomenon. Outliers are a necessary component. The way we build LLMs today, they're a necessary component for LLMs to produce accurate outputs. So these outliers, because you have these outliers, then it's not the case that just all of these rounding errors will average out. When you have these really extreme, very large numbers, then they don't tend to average out with everything else. Okay, so that's just post-training quantization, the really simple thing where you say, yeah, I've got a bunch of weights, and let me just change them from 16 bits to 4-bit numbers. Okay. Yeah, so I jumped the gun. So one of the things they say here is that outliers in activations are ubiquitous. Okay, so once you get a big enough LLM, you get these activations that are like orders of magnitude larger than other numbers. They mention a few different papers here you can look at for post-training. So if you're just given a model, it's trained already, then GPTQ, AWQ, QIP. There's also LLM int 8 and smooth quant. And there's a couple more slides talking about smooth quant. If you want to do post-training quantization of the KV cache, here's another paper, KV quant. And then a little bit more in terms of smooth quant. The idea is that you have these really huge numbers. Like I said, you've got a float 4,000, sorry, a 4,096 dimensional vector of floats. But it turns out that what people have observed is the really large numbers tends to always be in the same channels. So maybe the third of the 4,096 has some large values, and the 1,000th of the 4,096 has some absolutely huge numbers. But the other, 3,900 of them, they're all like kind of normal, whatever. So if you sort of keep track of like which of these channels can have really big numbers and deal with them, I don't remember the exact details how they do it in smooth quant. Then basically what they're saying is you can rescale those special channels, and so then on the right it's like now everything looks like they're all between 0 and 1, and then it's very easy to quantize. So that's the general gist, is if you could convert the picture on the left with some huge spikes to look like the picture on the right, then you're in really good shape. And then they have some results for smooth quant. Okay, so then the other thing you can do, this is the one that I don't really feel like I 100% understand. You can do quantization aware training. Okay, and so then the idea is that at a particular calculation, you can run the normal calculation, and then you can run the calculation to say, if you were doing 4-bit quantization, then here's how you would bucket it into 16 values. Here's the value we would have instead of my actual accurate precise value. Okay, and you can see where the errors are, where they're bigger, where they're smaller, and all that kind of stuff. And this is the part that I don't quite know exactly, but they say basically you store everything at high bit width and you fake quantize them so that you can see what's the difference between sort of quantized and not really quantized. And then you can do certain optimizations to say, where I have big errors, let me try and change the weights. I won't just use the vanilla quantization. I will try to minimize those deltas. And so if you do that, then that means that when training is all done at the very end and you need to bucket your numbers, you've already been watching to see if any of the bucketing will cause problems. And you've hopefully been able to sort of steer the weights away from those. And so it works a lot better. You get a lot less drop off from the quantization, but apparently it's much more expensive to run quantization aware training than just to do regular normal training. So it's pretty rare to see that done. Yeah.
Did you read, is this something that's done as a fine tuning, or is this the full tuning or training cycle?
I believe what they're talking about here is the full training cycle. There's another option which you bring up, which is fine tuning, which is basically, let me quantize. Let me do a very small fine tuning step on some sample data that I've curated, that I've chosen. Okay. And I'm just going to do normal back propagation. But again, any place where the rounding might have introduced some errors, hopefully this fine tuning will help blunt some of those errors. It'll correct the more obvious type mistakes, because you'll get fairly big deltas that in your gradient, in order to know. So that's that. I don't think there's a slide on that, but that's the other way that that people do it. But if you do quantization aware training, then you can convert your 16-bit weights to like 4-bit and know that you're actually going to get pretty good results without even having to fine tune.
Right. Gotcha. Thanks.
They also mention BitNet, which uses just +1 or -1, just two possible values. And then there was this paper recently, this 1.5-bit LLM, where they use -1, 0, and +1, which is kind of crazy. It's an interesting paper. Basically, they showed that if they use these ternary weights, so every weight has a scaling factor, and it's either -1, 0, or +1. So I don't know how you figure out sort of the storage for it. But it's kind of crazy that it actually works, that like, you're multiplying these things and you just have -1, 0, and +1. But it turns out that multiplying by 0 is very fast. Multiplying by 1 is very fast also, right? And then multiplying by -1, you just flip the sign. So it's actually super fast also. And so you could theoretically have NVIDIA build support for these ternary multiplies, and you could do just an insane amount of them per second. What they did when they built this 1.5-bit LLM is they said for the same number of parameters, we were actually able to get the same performance. I don't remember how big they got, but so let's just say like 7 billion. They built sorry, I don't remember exact details, but they basically built a really, really big model that used these really tiny ternary weights. And so they basically had like more of them, and they said that it got to the same performance. So I could be misremembering this, but what I seem to recall is it's the same amount of storage for weights. They actually had more weights because each of their weights is smaller, something like that. And then this other one I'm not familiar with, LMQAT. So they have some slides here on this 1.5 bit. I don't know that I found these slides to be very intuitive. So I'm not really gonna talk about them. But again, the idea is that these operations can be really fast. And so if you had hardware support, so it's plausible that, you know, while you might need slightly more weights of these really tiny weights, um, you still might actually run the models and train the models faster because, sorry, not train, run the models faster. I think training involves some funky stuff because you can't do gradient descent on just a 0, 1, -1, right? You have to have like floating point numbers. I think this business of ternarization happens after training. All right, so for time purposes, I went through this kind of quickly, but basically, quantization, it's going to work best if you have hardware support, efficient kernels for this. Generally speaking, you're not reducing the number of floating point operations um, uh, because the number's the same. What you're doing is you're just reducing the amount of memory. You're adding some flops due to like this quantization, dequantization business. And then Roger, I apologize. You had asked a question. I had said there was a slide coming up, and I may have misremembered, or else I may just have forgotten to cover stuff on the slides. But basically, yeah, like the main ways in which you work with quantization is you either say, I'm just quantizing to save on storage, and then once I'm done with like reading it out from memory, I'm just doing all the math as like 16-bit floating point numbers, whatever, and everything kind of works as normal, but I got a little bit of a win because, I'm using less storage. The other way of doing it is to say, no, 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 especially once you drop below 16-bit, now you're doing integer math. The integer math is very fast. So then that means that any outputs you have, because remember, you have like scaling factors and stuff like that. So if you say, I'm representing my numbers as like integers between -7 and 8 really means 1.35, right? So you have to like keep track on the side that 8 means 1.35. And then when you go into your next calculation, you have to make sure that like you're doing everything appropriate with your scaling factors, but you're taking advantage of just the integer multiply unit instead of needing to do floating point multiply. So I don't think I covered that very well, but there are two like very different paradigms, whether you're doing ultimately just quantizing storage and 16-bit multiply, or whether you're trying to do integer multiply on the GPU itself. Yeah, Jayanth, you have your hand raised.
Yeah, what do they mean by hardware support and efficient kernels? What kind of hardware support?
I think what they're saying is that you could manually do various steps around quantization and dequantization, but if NVIDIA built it into the GPU, then it would run even faster than you manually quantizing or dequantizing where you need to.
I see. So, got it. Thanks.
If I'm not mistaken, I think there's a format called NF4, just like how you bfloat 16, which is different from float 16. So for 4-bit quantization, there was a special NF4 data type that was proposed, I think, by Tim Detmers or in some research that one of those guys did. And
No.
there is a possibility that NVIDIA has looked at that and maybe including that, or is already including that. I don't remember that part.
No, that's great. Yeah, I completely forgot about that. So if you are doing the symmetric, when we talked before about like is it symmetric, is it asymmetric, and is it even buckets? I don't know if we actually had a slide on it, but whether you have even buckets or not, if you do symmetric even buckets, then it just works like normal integers. Okay. So if you have integers between -7 and +8, and you multiply them by other integers that are between -7 and +8, and you get your end result, then basically you can multiply the two scaling factors together, and the end result basically, you know, it just works like normal math. What Dave was pointing out is, what if you don't use that? What if you use asymmetric? Or in the case of Tim Detmers, yes, he found that in an LLM, a lot of the I think it was weights are not evenly distributed between the max and the min value. They're actually clustered more towards the center. It's a little bit more like a normal distribution. So what he did was he created uneven buckets where near zero, the buckets are smaller, and then the buckets get bigger towards the tails. And that actually caused less rounding error, because essentially what he was trying to do is to have 16 buckets that each had roughly the same number of numbers in them, instead of having a lot of numbers just in a few buckets and few in the tails. Now you cannot say that if you represent these buckets as integers -7 through +8, and you multiply them together, that like 3 times 3 is 9. You can no longer say 3 times 3 is 9, because these are these unevenly spaced, weird, spaced according to like, Z values. And so then that's where you absolutely need hardware support. You also need hardware support even for things like what floating point. If you're not using IEEE floating, well, if you're using IEEE floating point, you need support for IEEE floating point. If you're using brain float, which has a different breakout between how much mantissa and how much exponent, then you need support for, I think that brain float has more exponent than IEEE. Yeah. So like these are the things that you absolutely need hardware support, separate from what I was saying is probably not as relevant in terms of like the actual quantization steps.
Is that in the silicon itself, or is that
Yeah.
in the CUDA
Yeah.
library or something like that?
No. You need it in this. Well, okay. So you can have it in the silicon. Sorry, you can have it in the CUDA library, but then it doesn't run very fast if it simply says, "Oh, you're storing your data in brain floats. I'm going to do all this work to convert it to an IEEE 16 float, and then do the matrix multiply, and then before I store it, I'm going to turn it back into a brain float." That's actually going to run slower, right?
Mm-hmm.
You
Yeah,
need
I mean, I
silicon
guess the
support.
advantage is memory there, but the computation is slower.
So at some
Okay,
point, I
yeah.
can't remember what it was, but basically, like if you use a Google TPU, it supports BrainFloat. If you use an NVIDIA GPU, that does not support. It only supports
see.
IEEE 16. So
I see.
it supports FP16, but not BF16. And so
I
then,
see.
yes, you could say that there's CUDA software support, but it's just doing awful conversion back and forth under the hood and slowing you down tremendously.
Mm-hmm. Okay, cool. Thanks.
So yeah, we're talking about silicon support. So, and even like my 3090, I think has 8-bit integer support for quite a heavy amount of matrix multiplies, but not 4-bit. And then I think the 4090, you can actually say if you have tons and tons of 4-bit integer numbers, then you can saturate and really pound out a bazillion of them per second. So every generation, the hardware companies have to decide how much silicon real estate are they going to allocate towards 8-bit integer multiplies 4-bit, this new normal floating point for all that kind of stuff.
Cool. Yeah, I mean, like when I've tried the Llama Q4, Q8, whatever, I haven't come across any issue with the GPU, but but maybe I haven't tried something really wonky out there.
I think that when you do something like LoRa, ultimately you're just doing the storage trick, and all of the math in the GPU is 16-bit.
Okay.
So you're not trying
Okay.
to speed up the computation, you're just trying to reduce the amount of memory you need because these LMs are so big. If you want to run on consumer hardware, a 16 or a 24 gig single GPU, that's where like doing 4-bit quantization, you can actually get stuff to fit on a single GPU. But you're not really trying to speed up the computation, you're just trying to get stuff to fit.
Yep. Yep. Cool. Thanks.
All right. So I underestimated, there's this, I really don't want to go a whole nother section. So if you guys are willing to stay a few more minutes, I'm going to maybe do short shrift, but distillation, there is nothing here that's unique to LLMs. This is just basically everything you can read in any standard literature or blog about distillation. So can you have a smaller model? Can you distill it down? And so you have a teacher, you try and train the student. Typically what happens is the output of an LLM, if you have a vocabulary that's 40,000 words, then the output of the LLM is 40,000 numbers that all sum to one. It's the probabilities of each one of those 40,000 tokens. And so that's a discrete distribution with 40,000 values. And so generally speaking, you do something like you're using that distribution as the reference from the teacher, and you want the student to try to mimic that distribution of 40,000 things. And when you're calculating the distance between two probability distributions, the default will be KL divergence. And so I think you'll see somewhere coming up how to match uh somewhere uh uh I might have missed it, but basically you're going to do like KL divergence on the distributions. It doesn't say. Anyway, so then there's a bunch of research papers where they had other ways of measuring how far is the student from the teacher, not just that output distribution. Let's look in other places, okay? And so then you can see here, um, they add an L2 loss in addition to this cross entropy loss, and then here minimize the distance between intermediate activations. So again, we're not just going to use the final output. At intermediate points, we're also going to want to reduce the distance. So there's different more advanced tricks, and I'm not familiar with these, so I don't know exactly the details of how much better they work in terms of getting the student to, even though it's smaller, to hopefully be as close to the accuracy of the bigger teacher model. So, okay, so here's where we talk about like the KL divergence between the distributions. And so anyway, it's difficult. What I would say is the general conventional wisdom is that OpenAI is doing model distillation. We don't know what they're doing, how cutting bleeding edge they are, but you have GPT-4 and then you had GPT-4 Turbo, and if you noticed that it could output more tokens per second, and therefore OpenAI was able to charge you whatever, a third the price per token. And then 4.0 came out and it was able to output yet another whatever, 4 times as many tokens per second. And so then they were able to drop the price in the third again or whatever. The only way that those things can be feasible is if these models are smaller, if they have distilled GPT-4 into whatever that initial one and now 4.0 and so on. Another topic is pruning. Pruning's been around for a long time, but it's been difficult to get anything to work empirically. So the idea is you remove some of the nodes and then you don't have to do as much math, but then how how do you actually take advantage of this? If you do it unstructured vanilla, you can just say like, hey, I did a test and this particular node never has any large activations. I don't think it's contributing very much. If you have random sparsity, then it's just very hard for the GPU to benefit from that, since they're doing these large structured matrix multiplies. So I think a lot of the research has been, can you have some in between where you have a certain amount of structure you enforce? Obviously, something like block diagonal would be like the really, really best, but there are other things that are above my pay grade, where people have certain levels of structure. And so one of the things they talk here is something that I've never even seen before. Where is it? But here's this sheared llama. So yeah, so here they're saying like, what if you had structured, so there's n of m sparsity. So basically where it's like, so one of two sparsity would basically be saying that like, out of every two weights, you have to get rid of one of them. You have to get rid of half of them. And so you can have in silicon hardware support that basically has like a certain amount of pointers and blah, 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 blah. And it basically will figure out how to do this multiply where it doesn't bother wasting energy trying to do the whites because they're all zeros, but it'll do the greens, and it'll do it faster than if you did a dense multiply of all non-zero, all green values. So I did not know this, but you can see this diagram here that says you multiply this and it basically compresses it and has a bunch of pointers and figures out how to remap everything. And so it's not as fast as if you had an actual smaller matrix, but it is faster than if you had a full matrix. So yeah, so apparently NVIDIA actually supports this 2 of 4 semi-structured sparse matrix multiply. Pretty crazy.
Does this require like each row have, in that example, 4 elements and others are 0 or something? Like there's some
Yeah, I
sort of
think if you look
pattern?
at it, if you look at this, you'll see that this is an 8 by 8, and every row and every column, well, every row seems to have 4, not necessarily every
Right.
column.
Right. I mean,
Yeah, but
basically, that you scrunch it up into that 4-column matrix on the right, I guess.
oh, actually, no, I think it's actually very simple. It's in the rows, every 4 exactly 2 white and 2 green, 2 zeros and 2 non-zeros.
I see.
It's not even 4 total across the 4 can't all be on the left. It has to be literally every 4, I don't know what you call them, cells. 2 of them are zeros and 2 of them are non-zeros. And then yeah, it took out all the white space, it scrunched it, but it kept some pointers or whatever so that it knows how to unscrunch when it finishes the results.
Hmm.
It's just, yeah, I'm sure
Crazy.
some cool math as to, you know,
Mhm.
what's the relationship between multiplying by the scrunched instead of the original,
Mhm.
and then how you get it.
Yeah.
But yeah, pretty crazy. So
Yeah.
it's still pretty difficult. And so then they mentioned this one model, Wanda, where I believe what they do is they actually do optimization in order to try to find the best. So they basically say, I don't know, this optimal brain damage problem, but basically, so like if you're doing 2 of 4, then basically it's a constrained optimization problem where you assign 4 flags and you have to have 2 1s and 2 zeros, and so then you can just run this optimization problem to say, how do I find the maximum result for this? And so this Wanda thing, ideally what you want is you want your performance to be as close to the full dense model. And then of course all of these are smaller, are worse, but then the question is, are you close enough for the amount of compute savings, the speed up that you get? And this is not my area. I think the results are sort of mixed at this point in terms of, I think they say somewhere here, it's like a 1.24 speed up. So you can do 5 tokens in the time it takes the fully dense model to do 4 tokens. Like, I don't know how. I mean, I guess to OpenAI, that would be worth billions of dollars to get a 24% speed up. So, but for most of us who don't have millions of users every day, it seemed to me like those speed ups are sort of not overwhelming. There was another model where I think they said it had a something %% speed up. It's like, ooh. Okay, so then the last topic, and I apologize, I know we're over time, but this is a really interesting topic. It's been around for a little while. Speculative decoding. So what we talked about with the prefill is that if you know that you have 3,000 tokens, you don't have to do them one at a time. You don't need the individual predictions. Okay, so what you can do is if I say, what is the capital of France? And I run a smaller model, a smaller LLM, and the LLM says, I think that the answer from the big model is going to be the following set of tokens. The capital of France is Paris. Okay, so however many tokens that is, 8 tokens or whatever. What you can do then is you can feed all 8 of those tokens in simultaneously to your big model, okay? And so then basically you can see here they have the small, they have a different, I should have just used one on the slide. So KDD is hosted, or sorry, KDD is, and the small model guessed the next tokens were hosted in Long Beach. The big model, when you pass in hosted in Long Beach, actually says hosted in Barcelona, blah, 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 blah. And so basically what happens is hosted and in matched. And so you don't have to actually do 1 token at a time inference. They've already been confirmed. But because Barcelona didn't match long, you cannot use long or beach anymore. You have to then say, okay, I can pass in hosted in Barcelona and ask for the next thing. So so that's the general gist of speculative decoding. It's kind of clever. If you get into the math a little bit more carefully, then what you'll see is the vanilla thing is just we showed, like, did Barcelona match long? It's used in reinforcement learning a bunch, but there's this idea of rejection sampling. I think it also comes up in like MCMC, Markov chain Monte Carlo. But basically what you can prove is that mathematically, if you do rejection sampling, then you're going to get the exact same probability distribution for all the tokens output. And so then the trick with speculative decoding is you need sort of 2 basic things. One, you want your small model to be as close to the big one as possible, as accurately predicting the next set of tokens. Because the more it gets right, the more your speed up. If it gets the next 10 tokens right every time, you're going to get like a 10x speed up. Okay, so you want it to be really right, but at the same time, you want it to be as small as possible because the faster it is, the more helpful it is. If it's just as big as your big model, then you're adding extra overhead. You're not actually winning. Okay. So there's a couple more slides here that just sort of talk about rejection sampling, and then this idea of the small model they call the draft model. Again, you want it to be as fast as possible, but you want it to be as close to the big one, as accurate as possible. Generally speaking, you're going to see it says in the same family. Minimally, you have to use the exact same tokenization scheme. So that's, and then also same family likely to produce more similar outputs. So, you can use a tiny llama. I don't even know if there's a tiny llama out there that's been released, but a llama 2 billion to predict what's the output of your llama 70 billion. And that's the general gist of it. So, and then if you want to get really crazy, you can actually have multiple guesses from your small model instead of just one guess. So that if any of those guesses match, then you can keep kind of following that path. But it's a clever idea. And if your small model is cheap enough, then you can afford. But what you don't want to do is you don't want to predict, say, 500 tokens out with your small model if the odds are you're never going to use more than 5 or 6. So then you're just wasting a bunch of computation doing the next, 495 tokens. So you want to kind of like predict out far enough to get benefit, but not too far that you're just fooling yourself. You're predicting a bunch of completions that you're never going to wind up using. So I don't know I don't know speculative decoding that well. My guess is that in reality, you're somewhere less than 10 in terms of how many tokens out you're predicting, because you're usually only going to be right a few tokens out. You're not going to be right far, far, far in advance. And then the key thing, this line up here, it's lossless. You can prove mathematically that you're getting the exact same result as if you use the base LM in normal default 1 token at a time decoding. So that's it. So thanks for sticking with this. And we'll wrap things up here in terms of the formal presentation. And then I think we'll have a little conversation about what we want to do topic-wise for next week. But I appreciate those of you who stuck things out today. And then if you've been here for the series, thanks for watching all 3 parts.